Moving on to differentials. I went ahead and wrote some notes down here. dy, the differential of y, is a function of two independent variables, x and dx. Dx is exactly the same as delta x that we have talked about before, change in x. Dy approximates delta y, the change in y given a change in x. There's the blue box definition. So here's the picture. Dx and delta x are the same. Dy is the distance from old y to the tangent line, the change in the tangent line. Delta y is the distance from old y to the actual curve. So dy is approximating that change in the curve given delta x, the change in x. So let's look at example 3. We want to compare, in this case, delta y and dy. And our f of x, or y, is given by x cubed plus x squared minus 2x plus 1. That means that f primed of x is 3x squared plus 2x minus 2. So first, for part A, let's calculate dy. dy is equal to f primed of x times dx. dx in this case is the change in the x's, and the change in the x's is 2.05 minus 2.05. My x is my starting value for x. It's 2. So dy is equal to f primed of 2 times 0.05. And f primed of 2, I'll take a moment and plug it in and then meet you back. So I did a little multiplying, and the derivative evaluated at 2 is equal to 14 times delta x, or dx, and gave me 0.7. So dy is 0.7. Delta y is the actual function evaluated at 2.05 minus the function evaluated at 2. I went ahead and plugged that in the old calculator. So the function evaluated at 2.05 is 9.717625. Minus 9. So my actual delta y, which I was estimating with dy, is correct to 1 decimal point, 0.07. Let's do, this is A, let's do B. In this case, my dx is the change from 2 to 2.01. My x is still 2, so dy is equal to f primed of 2 times 0.01. So 0.14. Delta y is equal to f of 2.01 minus f of 2. Oh, how about that? I already have those in my calculator too. So it is 9.1407. 01, yeah, 01 minus 9, so 0.140701. So we were correct to, we could even say 2 decimal places. because we're even a better estimate. So the closer you are, the smaller your dx or delta x, the closer your dy is to your delta y, the better estimate you have, which makes sense. There's the pretty solutions. Okay, let's look at an application example. Radius of a sphere was measured and found to be 21 centimeters. Radius equals 21 centimeters. And they have a possible error of 0.05. So that means dr, my error, is 0.05. What is the maximum error in using this value to compute the volume? So we're trying to find dV. In order to do that, we need a V primed. In order to do that, we need a V, volume of a sphere, 4/3 pi r cubed. So V primed, 3 falls down, cancels with that 3, 4 pi r squared. So my differential of V is equal to V primed times the differential of R, which is 4 pi. My radius was measured to be 21. My differential R is 0.05. And I've already plugged all that in the calculator. It's about 277. And since it is the error in volume, volume is measured in cubic centimeters. If you're keeping up with those things, we have square centimeters times centimeters, so we do indeed end up with cubic centimeters. Now that looks kind of bad, so let's talk about relative error. Relative error is actually delta V over V, but we're going to approximate it by using the differential for V, and the differential was 4 pi r squared dr divided by my actual volume, which is 4/3 pi r cubed. So let's simplify that thing. 4 cancels with 4, that 3 comes up top. Pi cancels with pi, and I'm left with 1 r in the bottom and a dr up top. So my relative error in this case would just be 3 times 0.05 divided by the actual radius, which is 21. And I've also already plugged all that in. 0.05 over 21. Relative error of about 0.007 inches in the volume. So what we have written here, dr over r, is just the relative error in the radius, and we multiply that by the 3. That gives us the relative error in the volume, which is about 0.007. And then the percentage error, just write the relative error as a percent. Okay. Number 33 talks about a cube. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeter. Use differentials to estimate the maximum possible error, the relative error, and the percentage error in computing the volume of the cube and the surface area of the cube. I'll do A, I'll let you do B. So, yay, it's a cube. Cubes are easy. There is my cube. It is a perfect square. This side is x, this side is x, and this side is x. So the volume is x cubed. The edge was found to be 30. So x is 30 centimeters. The possible error was 0.1. So dx is, gave it an extra 0, 1/10 of a centimeter. So dv is going to be v primed dx. V primed is 3x squared dx. 3 times 30 squared times 0.1. Job for the calculator. Get out of the table. 3 times 30 squared times 0.1. 27 cubic centimeters. Now let's find the relative error and percentage error. So relative error again is going to be estimated by dv over v. dv was 3x squared dx over x cubed, which just leaves me with 3dx over x. 3 times dx, and I did 0.01 there again, so I'll have to go back and fix that number. Okay. 3 times 30 squared times 0.1, not 0.01. Yeah, that should be 270. At least I caught it before I uploaded the video. And then we have 3 times 0.1 divided by 30. So that's my relative error. That means my percent error is just 1%. Not too bad. So give part B a try, and we'll meet back here and compare answers. How'd it go? So we have 6 sides. They all have an area of x squared, so 6 times x squared. We take the derivative of that. We multiply it times the differential of x, which hasn't changed, and we plug, we chug, we get at most 36 square centimeters error, which the relative error is just 0.67%, so that's a pretty good estimate. Okay, number 34 I'm going to leave for you to do on your own. I'll post the answer to it. I'll do number 38 with us together because it's a little different. So we have one side of a right triangle is known to be 20 centimeters long, and the opposite angle is measured at 30 degrees with a possible error of plus or minus 1 degree. So I'm going to take a minute and draw a picture. Okay, I kind of lied to you there. I didn't just draw the picture, I did the whole problem, so we'll talk our way through it. Alrighty, here's my pretty picture. We have the one side has been measured to be 20 centimeters, and the opposite angle measured to be 30 degrees. 30 degrees is pi over 6 radians, plus or minus 1 degree, which would be plus or minus pi over 180 radians. And I asked the SOHCAHTOA hippie if what function I should use. I have theta, I have opposite, and I'm talking about the hypotenuse because I want to estimate the error in computing the length of the hypotenuse. So opposite hypotenuse gives me sine. Sine is equal to 20 over z. So I just rewrote that. I multiplied both sides by z, divided both sides by sine of theta. So z is equal to 20 over sine of theta, which is 20 times cosecant of theta, which is something I know how to find the derivative of. So the differential of z, my hypotenuse, is equal to z primed, so the derivative of 20 cosecant theta times d theta. So negative 20 cosecant cotangent times d theta. So negative 20 times cosecant pi over 6, because my original theta was pi over 6. Cotangent of pi over 6 plus d theta plus or minus pi over 180. I did some arithmetic. Cosecant of pi over 6, cotangent of pi over 6, plus or minus, and I ended up with a number. And then I just plugged it in to get the relative and percent error. You have all the knowledge that you need for your test. Go forth and study.